Welcome to The Explainer. Today, we're diving into the invisible, microscopic battles that let scientists pull apart impossibly complex chemical mixtures. We are exploring the fascinating world of chromatography, and specifically, we're going to zoom right in on the real unsung hero of the whole process, the mobile phase.
Okay, let's kick things off with the ultimate question. How on earth do we pull apart things we can't even see? Imagine having a wild mix of incredibly fragile proteins, or maybe super complex hydrocarbons, all jumbled together in a single tiny drop of liquid. How do scientists perfectly separate these invisible molecules out so they can study them one by one?
To answer that, we've got a quick roadmap. First, we'll look at the chromatographic tug-of-war. Then, normal versus reversed phase. Next, controlling a ludotropic force. And finally, the four analyte-solvent interactions.
All right, let's jump straight into part one, the chromatographic tug-of-war.
Think of your analyte molecule, the specific compound you actually want to isolate, as the prize in a massive game of tug-of-war. Its retention factor, which we just call K, is totally dictated by how strongly that analyte interacts with two opposing forces. You've got the moving mobile phase actively trying to pull it along, fighting against the static stationary phase that's trying to hold it back. If the mobile phase wins, the molecule moves quickly down the line. If the stationary phase wins, it stays put a lot longer. Mastering this balance, that is the literal key to the whole separation process.
Which brings us to our next section, normal versus reversed phase chromatography. This setup brilliantly illustrates the core duality of chromatography, because you essentially have two main choices. In normal phase chromatography, you use a polar stationary phase paired up with a less polar mobile phase. Or you can flip the script entirely with reversed phase chromatography. That's where you use a nonpolar stationary phase paired with a highly polar mobile phase, most commonly a mix of water with methanol or acetonitrile. The polarity of the mobile phase is basically the main dial we turn to control how fast our target molecules move.
And hey, this isn't just some abstract theory. It has huge real-world implications. Say you're trying to separate fragile, water-soluble compounds, like proteins. You absolutely cannot use harsh organic solvents because they'd completely destroy the proteins through denaturation. Instead, we rely on reversed phase columns and we equilibrate them with a concentrated buffer. By carefully, slowly reducing the salt concentration in our mobile phase, we can actually elute or wash out these fragile compounds completely safely, in decreasing order of their hydrophilic or water-loving character.
Moving on to Section 3, Controlling Allotropic Force.
We can actually visualize this manipulation by looking at the allotropic force, which is just the eluent's strength, plotted alongside the viscosity of different solvent mixtures. By mixing different solvents together, things like water, ethanol, methanol, or acetonitrile, we dynamically control the polarity of the mobile phase. You'll notice how the allotropic force shifts from weak to strong depending on the exact mixture, and whether we're dealing with a normal or reversed phase setup. We are quite literally adjusting the pulling power of the mobile phase on the fly.
For instance, imagine trying to separate hydrocarbons. These guys stubbornly stick to a reversed phase column like glue. So we start with a highly polar mobile phase where the hydrocarbons are strongly retained. Then, over time, we gradually decrease the polarity of the mobile phase. We might do this by slowly pumping in more and more acetylnitrile, creating an elution gradient. This gradient acts as a sort of chronological progression that slowly forces those stubborn molecules to finally let go of the stationary phase and start moving.
But what if your molecules are easily ionized and won't stay put long enough to even separate? Well, chemists have a neat trick. We can cleverly add ionic substances, like alkyl sulfonates or ammonium salts, directly into the mobile phase. Doing this induces dipole-dipole interactions that pair up with the ionic analytes, basically neutralizing them and rendering them less polar. All of a sudden, they become relatively stable, their retention on the reversed phase column increases, and we get a much cleaner, sharper separation. It's pretty brilliant.
All right, let's look at Section 4, the four analyte-solvent interactions. When we zoom all the way down, these are the four invisible hands of our tug-of-war. First up, we have dipolar interactions, which happen when both the solvent and the analyte have permanent dipole moments. Second is dispersion, those subtle interactions happening between neighboring molecules. Third is hydrogen bonding, driven by combinations of proton donors and acceptors. And finally, dielectric interactions, which favor the dissolution of ionic species in a polar solvent. Every single one of these specific micro-interactions fundamentally dictates how our analyte bonds with the solvent molecules of the mobile phase. So I want to leave you with this final thought.
Chromatography might look like some highly technical chemistry plumbing at first glance, but it's genuinely the art of quantum-level manipulation. By simply understanding and tweaking these 4 tiny molecular forces through our mobile phase, we unlock the incredible power to isolate, study, and utilize the very building blocks of nature. Everything from developing life-saving drugs to ensuring pure environmental samples relies totally on this microscopic tug-of-war. Thanks for joining me on this explainer, and keep questioning the invisible forces all around you.